Okay, so what I was saying is, as per the light hazard we are calculating, we are designing for, so the minimum design density in mm per minute is 2.25, which we actually used yesterday to calculate our first sprinkler flow. That gave about 47.25 liters per minute when we use design density to calculate the flow. Also, I told you we have two formulas to calculate the flow, that is the volumetric flow rates of the water at the farthest, at the last sprinkler head. So the second one we are using is the K factor multiplied by the pressure, that is the residual pressure expected. Then that pressure raised to the power of R, or you say the square root of that pressure in bar. So we got something around 56.57. So we are going to choose the highest of the two, which is the second one. So we are going with this flow rate. So what impact does this flow rate have on our design? So that means our P1 equals to 56.57. Then our, no, sorry, that's Q, that's not Q. That's Q1. Q1 equals this, Abi, liters per minute. Then the second one, which is P1, equals what? 0.5 bar. So we go to the second one, which is Q2. Q2 equals to, what should we do now? We are now going to do a pressure loss calculation. The pressure loss calculation is now going to give us the pressure that has been lost before going to this S4 that was in S3 before. So we are going to calculate the loss between S4 and S3. This line, which is 25 mm. 25 mm might not really have this 25 mm as the internal pipe size. So we have to check the catalog of the pipe we are using. Do you have any catalog of the pipe? Black steel. So, okay, I can say black steel pipe. Okay, let me just share the photo. So this one will give us, let me look for, okay. Let me just quickly see. I have a lot of them, but I don't want to be searching my admin. So what we are going to do to calculate the flow is we are going to calculate for the pressure first. So how do we get the pressure? In the P1, sorry, the P2 will now be equals to P1 plus pressure loss, that's PF, plus pressure loss due to elevation, so PE, PF, and BE. So pressure loss due to elevation, that is, if you have one part of the building higher than the other, you get, maybe you are rising, then you are dropping back. But in this case, we have a generally flat ceiling. So the PE for this project will eventually be what? 0. But the PL is the frictional loss, this frictional loss between this S4 and S3 according to the pipe, using which equation? As the William equation. So because of time, we have simplified it in an Excel sheet. Let me look for the Excel sheet. Just take it out. So we're going to say P2 equals to, what's our P1? What did we get for P1 before? 0.5 bar. Okay, I don't have to put the bar. Then plus, let's just say the pressure loss here. The pressure loss between the S4 and the S3 using 35 mm is, please wait, let me do this. I should use. I'm coming, please. stop sharing. I want to define how folio to sheet. So let me just show you the. So these are what software does. There's a software called Elite. Okay, so look at this one. For instance, if you have a lot of sprinkler you are considering, but you know our one sprinkler is not up to this. So we have the S1, Abi, which has the node 1, 2. So the flow that is entering it is this. So we have the node bar, which is 0.8 for this calculation. So what I just want to tell you is that there is a formula that we have actually placed here. See, this formula is what we call the As-Williams equation, which actually as in Williams. Okay. Okay, let me just write it here. So we have the as equation for pressure loss. You get it? This As-Williams equation is what you now use to calculate what is the loss in between that first one and that last one and the second to the last. So you are going to put the length, you are going to put the number of fittings, you are going to put look at it now. The internal pipe size for this 25 mm is actually 20. See, that means what we are actually writing that we are calling 25 mm is not even the external diameter. You know, we have 3 types of diameters. We have the nominal diameter, we have the inner diameter, then we have the external diameter. So that means that 25 is the nominal diameter. It's not the actual outer diameter. So the internal diameter cannot be more than the external diameter. So that means that 25 we have been writing is a nominal diameter, which is 25. So the internal diameter is actually 26.6. It's actually 26.6. So the pipe length, you are going to put it here. A moment, please. So I think I need to explain what the As-Williams equation looks like for us, so that we are going to know if we want to write it in our own, we want to put it in your own Excel, you can know how to do it. So let me just find it out here. I think it should be here. So here is the equation. See, so P is equal to pressure loss. So, and you know, pressure loss can actually be into units. It can either be in bar per length, or it can also be in bar. So if it is in bar per length, per unit length, then you are not going to be multiplying with this L here. Do you understand what I'm trying to say? Is it clear? Because if you do not multiply by this length, that means for every meter that it travels, it's going to give you the pressure loss. But if you multiply by the length, it's going to consider the whole length of the pipe and give you the answer straight. Do you understand? So P should be in bar, Q should be in liters per minute, your D should be in mm. Your C is a constant for the pipe material you are using. If it is black steel, it's actually either 120 or 130 or 140, depending on the table. See, we are being referred to a table here. See, it says C table 20 what? 22. We can go and check it later. So it also says that the L is the equivalent length of pipe and fittings in meters. So the equivalent pipe length, and look at it. If you are using cast iron 100, if you are using mild steel, it's 120. If you are using ductile steel 110, if you are using galvanized steel 120, if you are using cement 130, if you are using, but there's no CPVC here. So let's just, what pipe type are we using? Is there anybody online that can tell us the type of pipe we are using? The pipe type, the material of the pipe we are using for this our calculation. Anybody online?
Steel, right?
Yeah, we are using steel, but what type of steel? You see, there's galvanized steel, there's stainless steel.
That should be black steel.
Black steel.
Steel.
But black steel is not there.
Black steel. Should be black steel. It should be black steel.
Be black steel. You mentioned black steel yesterday, but black steel is not here.
Black steel is not here. So what are we going to do? We use the closest. Is that we use mild steel, that's 120, or we just look for another material that will tell us what type of what is the C constant for a black steel pipe. But I'm putting it to you that mild steel and a black steel is not that far apart in terms of their roughness. Okay, so if we want to, steel is not steel. So if we want to input, because we are actually supposed to do this class manually without using. So if you want to input, I don't want to go because this Excel is a little bit complicated. I just need you to understand it from the first principle. Okay, so how can we put this formula to our worksheet? Let me copy it. Let me copy this. Sorry, please. Select text. Yes, I can now copy this and put it in my workbook. This is our workbook, Abby. Hey. So it did not come out well. It's what you copy. I copied this formula. Okay, I should paste as seen. This is not Excel. Right click. This is the only option of pasting that we have. Okay, that is just by the way. So let us try and solve this equation. Who can solve this equation for us? P equals to 6.05 exponential 5 divided by 120. I want to try and put those C there. C raised to the power of 1.85, then multiply by what's the internal diameter? I think I showed you all the internal diameter, 26.64. Then multiply by what is the length of this pipe. So let us go to our Revit. So where is the most hydraulically remote area? This is the first floor. So we cannot use this one. Let's go to the second floor. So, you know, what we did yesterday was an automatic connection for Revit. So let us see, maybe Revit can actually generate the pattern for this one too. Yeah. Supply for this is from a tank. No, it's from the ground floor. But let us just connect it. I'm going to show you how to do that. Don't worry. So let's connect this, select similar. VCU. Now go to piping, connect it to a system, then generate layout. Yes. So this layout has been generated. Do we want it to be a network? Do we want it to be perimeters? I think I prefer network here. This network is not, we should use the perimeter. So let us look for another option. This is another option. This is another option. I think I prefer this. What do you think? Let us just say yes. And accept this layout. Okay. So is there any shaft that you people have been using to pass your maybe water supply, drainage? Okay, where is it? In between this one and this. So we can now use this one as where we are going to be connecting from. So let's have a section. I think this is it. So I can now have my pipe. What type of pipe am I using? Carbon steel. So I want to make it an 100 mm riser. 100 mm riser to supply to. Just do it beside this place. 100 mm. Let me stay clear. Let me stay clear of what I want to say. So come inside. So I can now see it here. Okay, I can move it. So this will not be our riser. You see now? This will be our riser. So is that we isolate each floor or we isolate each wing? We can make right and we can do it as a right and left wing for isolation. You know, there's something we call zone control valve. And that zone control valve is an assembly of so many valves. It's an assembly of water flow switch, butterfly valve, remind me of other valve that is there, a strainer, a pressure gauge, an isolating gate valve, a check valve. It's a lot of valves that is inside that zone control valve. So what it does is that it's isolate a particular zone for maintenance. Let's say you want to replace a sprinkler. Instead of you to just say, okay, I want to off the whole system, because you can just isolate that place you're using. So let's go to the ground floor. Do we have sites? Do we have sites for this? No site. No site ground. No site. Okay, so we're just going to come out from this place. Okay. Let me insert my fire pump. Let me bring in my fire pump. So sorry, please. Let me look for my fire pump. Look for my fire pump. Typical. Sorry, please. Okay, sorry, please. I'm searching inside the project. Okay, so I have a lot of fire pump here. This is 1, 2, 3, 4. So let me just use. Let me copy. Let me. You know that there are so many ways you can bring a family into a project. I think you have been taught that one. But instead of wasting time, I can just drag and drop. Drag and drop, yes. I prefer to do it like that. Okay, so this is a fire pump. Why is it okay? Close it with your okay. You want to save it? So let us just say we have a plant room here, but it's not showing. Why is it not showing? Let me make this place to be unlimited. I want this. Unlimited. We're not saying a fire pump. Let me look for it. We look for fire pump. Bring it to it. It's not showing. Why? Oh, I think we've turned it off. Look at it here. So let me it on. Yeah, God bless you. You remember we are the one that turned it off. So we go back to our view template, Abby. So we go to model. So we say mechanical equipment. Then we turn it on back. You see? Turn this on. Apply. Then it should show. I think we can create filter, but I'm not sure I want to do that now. Let me just. Yeah.
Okay.
We're supposed to. Okay, I'm coming. Okay, the reason why you show is for coordination. We should use it for coordination. We are still going to. No, we cannot delete it now. No. So let's go to filter. Let's go to- Okay, so we are now going to run our pipe from this shaft that goes all the way up to connect to our fire pump. So it is advisable because of losses to make sure what is coming from your fire pump is what is very high, as in the pipe size is very large, about 150 mm. So what we'll do now is there's no tank here too. So we need tank.
That's what I was trying to ask now.
No, the standard practice is that you should have both your bulk for water storage and for firefighting should be at the same place, so that you are not going to have a large volume of water sitting for, let's say, 30 or 50 years there without being used, and it's going to be very dirty, stagnation, and all of that. It's going to even be very, very green because of all this agri. So what we'll do is to combine the requirement for domestic water usage with firefighting. We add the two together. We now make sure that the height at which our suction pipe is, let me just draw it so you understand. So let me go to the view. Let's say a drafting view. So this will now be a section, a drafting view. I'm going to be showing you a section, let's say DL. So if this is our tank, if this is our tank, so this is our pump. Okay, let's say the pump is, okay, let me just extend it. Let me extend this line. Let me extend it like this so you understand where the natural ground level is. Let me extend it like this. So we have our pump here. We have our pump somewhere here. So we are going to connect for firefighting. We are going to connect it like this. Then you connect to somewhere here. So this is a fire pump. Okay, so let's do another one. Let's say we have a booster pump here for water supply. So you see where this one is sucking from, right?
Yeah.
So this one is now going to suck from somewhere around this place. You see the difference. So you can now measure the difference. You see detail. You can now measure the difference. Measure the difference. DI 220. You see now. So the volume of this 220 is the difference between the firefighting requirement and the water supply requirement. Hope I'm clear. Let me just give us an example. Let's say the water for firefighting requirement for this our simulation is 20 cubic meter. Then the water supply for the residents, for the usage, the domestic usage is, let's say, 15 cubic meter. When you add the two together, it's going to give you what? I say 15 and 20. That will be 35. Now, if you have a dimension of about 5, okay, what can give us 35 as a dimension for tank? Let's think about it. Let's say 5 by 3, 7 by 5 by 1. That's 35. Or we say, let's just go by that one. So this is our depth. Let's say the depth is 1 meter. So you are now going to say, how am I going to get 20 out of the 35? I don't go too much. Okay, so let's just do it like this. We have 20, Abi, and we also have 15. Abi, our proportion now, we want to use this ratio, 20 and 15, to divide the 1 into proportions. So that it's going to give us the volume for this and the volume for that. Do we understand what I'm saying? Yeah. So you're not going to say 15 divided by 35, divided by 35, then multiply by 1, because that's what you are actually doing, right? But that's what you're actually splitting to 2. So you're going to have 0.4 for what? For the 20 mm, for the 20 cubic meter. Is it 15 I did? Wait, I said 15. Wait. Where's our pen? So what I'm saying is, they said you should share 20 cubic meter, 20 cubic meter and 15 cubic meter in between 35 cubic meter. So what you are going to do is you say 15 divided by 35. Are you with me? 15 divided by 35 give you this, then multiply by 1. That's 0.42. That's the first one. This will be the depth for the 15 cubic meter, which is for your usage at home, your domestic usage. So if you now subtract this 0.42 minus 1, answer you get minus 1. That will now be 0.6. So it will now be 0.4 and 0.6. Do we understand? This is how I divided it. So you now be that your distance from here, if you are taking it that, look at it, if you are taking it that from here to here is 1. So this is not up to 1. Let me make it to 1. Let me increase it to 1. Let me make it to 1. It is now 1, Abi. So that will now mean that the one for domestic usage, which is 15 cubic meter, will now be 0.4. That will be 400, Abi. So I'll now say di from here to here. Are you with me, please? This will now be 400. Then the other one here will be from here to here. From here to this one will now be 600. Do you get it? So invariably, the suction of the firefighting will go further. I'm not even sure we are supposed to measure it from this natural. We're supposed to measure it from here. No, it's up. You're right. So let's just leave it like this. So what I'm just trying to say is that for firefighting, we have a deeper suction than for domestic usage. Okay, so what am I trying to say? We go to this place, we cut a section, go to our view, then take this one out. This one. I want to make this section to be just firefighting section. You don't have a firefighting section. I can just pick a firefighting plan. It will take off all those pipes that will remain my own. Okay. So I can go to this. Are we getting it? We go to this place. Go to my floor plan. View range. Why am I not seeing this one? Let it go out. We get it. Now go back to your browser. Also, the code states that any fire pipe that is passing, that is going to be buried underground, should be wrapped with what? A denso tape. So I'm not even sure this place will be. This is an entrance now. Abi, this is the entrance. So I'm not sure we're supposed to. So let's take it back. Let's take it back. Let's delete this one. Let's delete this. Let's delete this one. Let's delete this. So I can now select everything here. Then take it to this other side. The reason why I'm able to move it around like that is because it has not been connected. I can now move it back. No, it's not 25. I'm going to change it. We're not supposed to pass here. Yes. So it's underground. Okay. It's underground. is underground. You get. So what I was saying is that the pipe size, the bigger the better. So if you want to rotate any element that has been incorporated into your model, I think you'll have been taught that you use spacebar to rotate it around. Yeah. So now let's change the pipe size. This is 25 mm. I think because what we drew last was 25 mm. So let's change this to the main riser. Let's change the main riser to 100 mm. Now, what elevation is this? This one underground. So let me make it minus 300 under the ground. Now, let me bring in a family to represent my tank. I normally use a Mark O, but we don't know the size of our tank yet. You know, we have not done the hydraulic finish. We have not finished it.
And this slide, I really pass you. That's what I'm saying. Yeah. That's what I'm entrance.
It's underground.
It's underground, I'm saying.
Everybody is another. Okay, it's not to more.
Okay.
You can take it towards the left hand side.
Like this.
No, this side. Yeah,
I don't want to pass through this mechanical.
yeah, just come to this other side.
This place.
Yeah.
But is there any reason why you don't want us to pass? It's another ground now. Yes. It's surface. This fire pump is surface. So no. So what is going to happen is this. Let me just draw a sectional view for you. So we are going to see something like this. DL. This is the pump. Yeah. So the suction side of the pump, DL, the suction side of the pump will go like this. Go into the tank. If the tank is underground, we get. And the discharge will go like this too. Go down. You see, go down like this. Enter into underground. So let me do DL again. So this is the natural ground level, this place. Do you understand? So TX. This is too big. Is it the scale? Okay, now let me do this. No. Okay, 50. I mean, so TX. So this will now be natural ground level. Do you understand what I'm trying to do? So what I'm saying is, if this box here, TX, is our fire pump. Let me reduce it to sorry. If this is our fire pump, you know, fire pump has, every pump has two sides. We have the discharge and the suction. So this side is the suction. So if you want to, let me do it like this. So the fire pump goes like this, then enter into where the suction is, where your tank is. So this is our tank here. Look at it, please. This is our tank here. You see it? So the fire pump reaches somewhere here. You see, this is the suction. This is our discharge. This one, look at it. It's going under the ground. I think I need to do something like this. So it's not what I'm saying. So this is underground. So it's not going to affect it. This is underground, but it's not going to come up here. Just before the pump, it's going to come up. Come up like this. This is it. Then join the pump here. So this is the only thing you're just going to see this elbow coming down, going into the ground, then going like this. The fire pump is outside now.
That's
Yeah.
this now. It's not really like.
You know, we don't have a, we just It's just indicative. You can put it anywhere. You can put it here. Okay, so if you want us to put it here, we can put it here. There's no problem. We don't have a utility rule.
You can maybe where you have your course.
It's better. But there's something here.
Then you can maybe place it.
This is just indicative. There's no. We are not constructing this building. So if you want to put it here, there's no problem. So let us just connect it. This is, don't forget that the elevation of this one is minus 300. That means everything here is underground. It's underground till this place. So it cannot rise here to about 250. Where it's not going to join with the pump. Do you understand? It's going to connect to the pump. So we might not be able to connect it now, but I'm going to show a section of where we are going to connect it. So let me draw. So when you are connecting to a fire pump, you need a lot of families. Family like butterfly valve, check valve, water flow switch. So you see now, this is our rise. You see, so this way is entering into the underground level. So let's see which one is the discharge. So this is the discharge. So we can go like this. So the discharge is usually at the top side. So we can now connect this one to this one. Yeah, that's our discharge. Yeah, this one is going down. So let me check. It's a very massive fire pump. Why is it not? The fire pipes are not showing here. Okay, it's a mechanical distance. Wanted to say something. Fire plant. You see? So we can adjust this. We can adjust this connection better. So we do. You see what? There's someone is asking a question. Which this one? It's a clash here, don't worry. So let me just move it like this. Then align. Then I can now trim the seat drop and rise. So we check it now. It is now well connected, Abby. So for every connection, because this place is supposed to actually be a plant room, so I can extend this one. Because of clashes, extend it and extend it. Okay. So we are supposed to have a butterfly valve and 2 check valves. So I don't know, maybe I can find that. Well, that is just that about the connection. We are not here to do a lot of connection. So this 100 mm going into the building, and we are going to connect. I want to find the best way to connect this. These are the things I don't like about using automatic connection for Revit. Look at it. It's wobbling. It's wobbling. It's not. Okay.
The source to connect the supposed to be like bigger and be reducing like that.
Yes, yeah, but the source, that's the main supply pipe, is supposed to be a one single pipe size. It is when you are now connecting that you can now be reducing. And then what you are saying in this Revit, if you do automatic connection for Revit, it will not reduce the size. It will just give you a one pipe size system. Yeah, look at this. This is 15. This 15. Everywhere is 15, and this is not right because of the pressure loss. Okay, I think we were doing something on pressure loss before.
Maybe for the source. To split it left and right.
We can split it, yes. We can 1, 2, yes. We can split it left and right. So that means we break it at this place. But there's no problem. Let's go to the second floor. Let's see what we can do. Okay, so we have our So how do you think we can do the zone control? We are splitting it to left and right. That means we are going to have two zone control valves. One will be controlling left wing and one will be controlling the right wing. Do we understand? Okay, so has anyone be able to solve this equation? We have 25 mm, which has an internal diameter of, okay, let me write it in red. 26 point, is it 4? 26.64 mm. Do you get that? So now going to our Azimuthal equation, I have a reason of doing that because we want to know the pipe that will be accurate for that. So now please let's do this. Let's do this. Our flow is what? What is our flow? Our flow is our P1 56.57 liters per minute. Let's do it. Let's see what our pressure loss will be. So let me just assume that the pressure loss is 0.01, let's say 0.03 bar per watt. I want you to confirm what I've written, bar per watt per meter. Do you understand why I said what I got is 0.03 bar per meter? Per length. So I'm now going to multiply by the length of this one. So what is the length from the here to this place? Let's go to our Revit. So which place are we considering as our most remote area? So let's say we are considering 1, 2, 3, 4, this place. So let me draw it DL. We are considering this place. This place. These are 4 sprinklers we're considering. I think we know how to do all these things now, have we? We did it yesterday. So this is the 4, 1, 2, 3, 4. So we are doing, this is our S1, S4, S3, S what? S2 and S1. So we are doing, so this place you are saying this 1 and 2 is what has been brought out in this place, S4 and S3. Do we understand? So after doing that, we continue. So please let us find the difference in the pressure between S3 and S4 with this formula. You can also put it in Excel. Yes. Maybe it's me that someone that did this one like this. I don't just want us to go through this one because it will be too cumbersome for us. Let's do it. So I think also I think I need to tell us too that let me go to where we're actually doing our detailing. Okay, so this is fire pump. So DL. So don't forget that if we have your main header like this, Abby, it will drop like this. Then to go and meet a sprinkler, Abby. This is not how it's going to be. It's going to be like this. Then the other one too will drop like this. Then meet a sprinkler here. Is that not? Yeah. Then this one too will continue, DL. It will continue like this. So this is our S1, this is our S4, this is our S3. Don't forget that there's an elbow here. That's what I'm trying to say. There's an elbow here. We have to account for that elbow too. We have to account for this elbow too. We have to account for this T. You understand? So let's go. So how do we account for those things? So the fittings are here. Look at it. Equivalent length of straight pipe for a C value of 120. So if you're having a 90 degree screw elbow standard, if the nominal diameter of that screw 90 degree bend is 20, then you are going to be using the length to be 0.7. Are you with me? Am I talking gibberish? Okay. I drew something in the section here. I said we shouldn't forget. Okay, let me write it. TX. Let me do something. Let me say I want my text to be red. Then I want it to be times Roman. Then I want this to be 0.8. Then I want the text to be bold. Then the tab size to be 2. I don't need any arrow. Let me say no. Okay. So now I can write here that this is E. Let me zoom in. This E. Okay, let's say 1E. 1E means one elbow. Are you with me? Yeah. This one is 1T. Let me write like this. Then, or we can also do it here. We can also do it here, depending on how imaginative you are. You know that this sprinkler will drop. It will drop like this. Then enter into this sprinkler. So as it's dropping, it's not even an elbow because it continues. Look at it. It's a T. So let's go back to okay, so we should draw a section. The reason why I don't want to draw a section is because we are not the one that drew it. I want us to finish this calculation. It was automatic. So it might not draw it right. Let's just check it here. Let's check it. We can check it. It's not this place. This is not the okay, so here is it. So this elbow is what we are accounting for. But you know, I'm coming. There is an elbow. Sorry, please, I'm getting confused somehow. Okay, the reason why it's showing an elbow is because it is off. Look at it. Look at this place. Look at this. It is off before now going down and now dropping to the sprinkler. It's not as if it is coming down from the sprinkler. Do you understand? Eh? Do you understand, Victor? So what I'm saying is, look at it here. There's a difference between something dropping from the header directly to the sprinkler and from it having initial T, then before that one I'm dropping down. Do we understand? So if you go back to this one, let me do so that to be sure. Look at it. So if you draw a section, you're going to see this one dropping down. So we have one elbow here, one T here, Abby. Yes. So we can now say in this TX we have one T, comma one E. One E. Are you with me? Do we understand how we get one T and one E? Ah, people are sleeping. Can we pause? Can we pause? So this is one T, one E. One T, one E is as a result of we having a drop here to the sprinkler. Can we see this drop? There's a drop here. Let me draw a section again, please. This is a section. This is a section showing us how it drops into the sprinkler. So this is one elbow. Are we clear? Yeah. The elbow is what I'm writing here, one elbow. Then there's another T that makes it to continue, which is this one. There's a T here. Look at the T. So you have to account for it. If you are using this 1, 2, 3, 4 is our assumed area of operation. What is the maximum? How do we get the maximum area of operation of the sprinkler? Who can remind us? So that we know that maybe I'm going to continue this class or I'm not going to continue it. Who is going to tell us online? If you have been following this class, how did we get this 4 spring class? And how do we know that we are going to consider just 4? Why are we not considering 5? Why not 6? Why you? Not you, not another person. Nobody is online. Okay, so if we are okay.
You know, we take the light hazard.
So
it was
4 that we were asked to consider. So let's go back to our guide. You see, for light hazard, we use 2.25 density, that's design density. Then the equivalent number of sprinkler is 4. So we did not consider this area because we might not be able to get that amount of area. So let's continue. So what is the distance between the 2 sprinklers? What is the distance? How can we get the distance? TG. So what I normally do is to do this. Then I will now edit this thing. Especially if you are doing for 5 that is very plenty like that. You now go to the length. You add it to it. Okay. Then you now see, you're going to see the length. You see, this is the length. It's better you do it like this. Because when I normally do sprinkler hydraulic calculation, the sprinkler you want to consider will be too much. You cannot be doing click one, check the length here. You waste your time. But by the time you just say TG, you tag this one, you know the length. Tag this one, you know the length. You see it? Although we are not going to use 15, this 15 is what Revit has generated for us. Because if we use 15, the pressure loss will be what? Massive. It will be too much. So we are going to be using 25. So don't forget we have a short piece here too. We are going to target TG. What is this short piece? So that's 0.1. Abi? Okay, so going back to our calculation, we have 0.03 per bar per minute, so per meter rather. So P will now be equals to 0.03 multiplied by what's our distance? Let's go back to our distance. Hope you know how I got 0.03. Ahead, if you use it as a Williams equation, slotting in this 1t, this, right? There's a lot of things to know. So these are the values for a screwed elbow, a welded elbow, a screw elbow. So I'm not even looking for the T. So you see a T, please. Okay, you've seen it, Abi. So standard screw T or cross. So if you are using a T and it is about 25 mm, Abi, so this is the equivalent length, 1.5. So the reason why we cannot slot in that equation directly is because of the varying length. I don't know, maybe you get. The lengths are varying, then the pipe size is also varying. So what you can do, people, some people are wiser than me, some people are not as wise as I do. What I normally do when I've not really done this template is that I'll go to this equation. Go to this equation. Where did we get as a winner? Yes. Up here. I will now do everything that is constant. You get. I will now make it a constant, like I will say 6.05 exponential 5 divided by 120 raised to the power 1.2. I will now leave the D, the L, and the Q. Okay, the Q2 the Q2 will vary. So I will now be using it to multiply a factor that we get when I use length to divide the diameter and multiply it by the flow. Do we understand what I'm trying to say? You have something. God bless you. I make the equation shorter so that I'm not going to be doing the same repetitive thing, because I know what will definitely be changing is not the diameter, the length, and the flow. So I'll just say 6.0 exponential 5 divided by 120 because see, the material is constant. It's the same material we are using. Do you understand that part? Yeah. Or you do it as an Excel where you can actually put in what the D is, what the L is, and what the Q is. At every point in time, it gives you the equivalent pipe loss, pressure loss. Do you understand? So why do we need to do all of this, Eddie? Why is this finger too hard like this? It's because you want to be sure that you are able to satisfy the recommended pressure of the manufacturer. Because if there is a fire and the sprinkler cannot actually extinguish or do not give you the required spread pattern that can actually extinguish, they will look for you. They will look for you. So I think we can go for a break now. In the next 15 or 20 minutes, how many minutes? Okay.
Hello, Mr. Ridwan.
Yes, who is there?
This is Emmanuel. Sorry. I just want to ask, for this head loss, is there no software for it, like for the chill water system? So if you wanted to calculate the what's it called, the pressure loss in the systems, whereby to get the actual, what's it called, the pump size for your system. I think there is always a.
Thank you very much. I understand what you're asking, and there is a software, they call it Elite Pro. We also have there are so many software you can use to calculate pressure loss in pipe network, not only in sprinkler alone, even in chilled water system, even in booster system, high-rise booster system. There is a software you can use. But because of the fact that we are going back to the first principle, that's why we are going through all this. And for the fact that I'm also taking you this class, I may not be opportune to have all those softwares too. So that's why we are going back to the first principle. So by the time you understand this first principle, you can slot in this as a Williams equation into your own Excel sheet that will now populate the pressure loss for you. Just like I've done in my own case here. Look at it. Do you understand? So what I just showed you is an Excel sheet. It's not a software, but those software are actually paid for.
All right, thank you.
Okay, so someone is telling us here that even if we don't understand these first principles, you might not be able to use those softwares too.
Yeah, I get that. All right,
All right.
thank you.
Okay. Yeah, thank you.